Alright, I hit the button. Hit the button, yes, okay. Starting to record, blah, 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 and such. So, live chat. And pop out the chat. And I have to make sure it popped it out. So, gotta waste a little time doing that. Should be somewhere around here. That doesn't look connected to anything. It should be correct. Alright, made the little thing smaller, but it's not showing, so I have to get that. Still isn't doing anything. It should do something now. There, now it did something. Alright, put that up there, I guess. Yeah, doesn't really fit. It'll have to do. Okay, I probably should have it below there. Alright, put it down there. Ooh, that didn't work. Should go the other way. Yeah, this way. Okay. That should be better. Alright. Okay. So, what are we doing? Yeah. So videos. We'll just play some videos from a channel. Actually, two different people linked me to this channel, something G or whatever. I think I've been here before, but it doesn't really matter. We're just going to play some of these videos that are Peak G, it's called. Okay, it's another one of these guys who's probably a, I don't know, high school teacher, and so he makes some videos on the side, blah blah blah, and these are mostly 10-year-old kind of things, I think. I don't think he's made anything recently. So anyway, 8 years old, whatever. So this one's called force multipliers, and it's really a bad, the verbiage used is really poor in terms of how words are used in physics. And so I would argue that the title of this video is correct, that it's force is momentum, and momentum is just an instantaneous weight or a continuous weight. That's all it is, and it equals energy because it's just made out of mass moving, and that's what energy is, mass moving. So you can play it again, please.
Right, so this is a quick introduction to force multipliers, which we touched on in today's lesson. Hopefully this will help explain
I'll fix that
and give you a few examples. So a force multiplier is a machine that multiplies force by a constant factor, a constant amount. So it's something that if you put in 2 newtons, okay, as your input force, the force you're putting in, you might get out 10 newtons is multiplied.
Alright, so it's just wrong. You won't get any of that. So I don't know why he's saying it that way, because that's not what you're multiplying. You're multiplying something that comes before the newton. In a sense, you're multiplying, either you can multiply how much something weighs and then diminish its velocity, or you can increase its velocity and you can change its velocity and increase its velocity and decrease its mass. But it's really just momentum conversion. So you're not going to be able to multiply a force. You can't. Okay, that's free energy. Or it's wasted energy in the opposite direction. So then you just can't. You can't kill energy, and you can't create it, and you can't destroy it. So we really shouldn't be using language like force multiplier, because it's not very useful.
Your force by a factor of 5. So 2 newtons in, you get 10 newtons out. If you then pushed harder and pushed 4 newtons as your input force, you would then get 5 times that out. You'd get 20 newtons out.
So none of this doesn't have anything to do with kinetic energy, in the sense that's not really what he's talking about. So it's not about the squared factor. It's just that he's calling, again, things like levers and hydraulics multipliers instead of converters.
Machine multiplies your force by a constant factor. In this case 5. It could multiply by 10, it could multiply by 1,000. This might sound a bit weird and that there's some sort of cheating afoot here.
Yeah, it does. This really isn't good. It's not logical. This isn't a good way to put these words together. Newton basically said force equals momentum. In the sense you want to, there's no multiplication. There's a direct proportional relationship between. You want twice the momentum out of something, then you have to double its velocity or double its mass. And doubling its mass, but doubling its velocity easy, and you just apply twice the force. Blah blah blah.
Because you seem to be getting more out than you put in, but don't worry, we'll address that shortly.
Yeah, so why bother with it? I mean, if you're going to address it, he doesn't address it shortly. He addresses it at the end of the video. He'll address it right in the beginning that we're really just talking about one of the ingredients that is the end product of force. And, we're going to multiply one of those ingredients, but to multiply one of those ingredients, you're going to, divide the other one by the same factor.
So, what are some examples of force multipliers? There are tons. You need to know about 2 in our GC.
Yeah, so there are tons, and, so there's the gears, big gear, little gear, levers, hydraulics. So he's going to go through 2 of those anyway, so we'll play through this just to point out there's no sign of this kinetic energy theory anywhere, no talk of it, no explanation that the end consequence of the theory is that frankly you do create free kinetic energy, and that therefore why are we pretending kinetic energy is real?
Yes, see, but there are many more. So one example of a force multiplier is a hydraulic system, which consists of 2 pistons.
So it would have been better if you used the 2-to-1 relationship instead of a 5-to-1 relationship. Just makes it more obvious, I think, to keep things, we all kind of understand half the mass, makes it easy, blah, blah, blah.
That are connected together and filled up with some hydraulic fluid, like oil, for example. And you will have been able to solve problems like.
So the good thing is that this, I did come upon this theory also in the sense of using hydraulics as an example of momentum conversion, and that this basic simple device essentially proves there's no kinetic energy because it shows you how you can simply destroy energy or simply make free energy. And it can't be that simple, obviously.
This. So if I put in, let's use a different colour. If I press down on this piston here, the small piston with 2 newtons, okay, you'll have learned that you can work out the pressure that exerts, which is force over area. So 2 newtons over 10 centimeters squared.
So the irony is this is the energy destroying by kinetic energy theory way of doing it. So it's still, he's going to say we've changed the force by a factor of 5, but obviously he hasn't. So the real momentum is just the same as it was before. And but if you use kinetic energy, you would recognize that these 2 newtons are at a mass velocity ratio where the velocity is higher than what your output is going to be. You're going to just change the velocity,
which gives us a pressure of 0.2 newtons per centimeter squared. You'll know that the pressure is the same throughout the whole. So
the centimeter squared has nothing to do with anything. That just has to do with the area of the cylinder you're pressing. How much area is it? How much fluid area is it pushing on? So it's more like a volume thing. That's why there's a square.
Hydraulic system. So the pressure over here throughout all of the fluid, the pressure over here is the same. The force over here is pressure times area, which is going to be 0.2 newtons per centimeter squared times 50 newtons, which is 10 newtons. we have multiplied the force from 2 newtons to 10 newtons.
So obviously it's like a backwards to the kinetic energy perversion. And this really doesn't mean anything because he hasn't accounted for the fact that the displacement, the motion, will be in a lot less in this case, which will revert the 10 newtons back to 2 newtons. So he's basically just pointing out that the momentum is going to be the same. He's just doing it badly.
Multiply the force by a factor of 5, and you'll notice that the area of the input piston and the area of the output piston are in the ratio of 1 to 5. Okay, so the ratio is 10 centimeters squared to 50 centimeters squared, which simplifies to 1 to 5. So the constant factor that this system will multiply by.
So there's no constant factor, there's no multiplied by, none of all that's just way more confusing than you need to state. You're just going to push on one side and it's going to move the cylinder at a certain speed, and that's pretty much all that's going to happen, and the speed here is going to be 5 times less.
Is 5. That means, I'm not going to do the calculation, but if I then put in 4 newtons, hopefully you can see that if I put in 4 newtons, the pressure will double. Therefore the pressure that goes into this equation will double, therefore the force will double. Okay, so if I double the input force, I double the output force. The ratio is still the same. It's always going to be a fixed ratio of input to output force, in this case a multiple of 5.
Right. So the input force and the output force will be the same because the force is the combination of the mass and the velocity.
Obviously, if I changed my hydraulic setup, if I had a larger output piston, then that would change my ratio and it would change my force multiplication. I could maybe change this to a bigger one, okay, 100 centimeters squared. Now my hydraulic system would multiply the force by 10 because the ratio of the areas is 1 to 10. So hydraulic systems, one example of a force multiplier, always multiplies the force by a constant amount.
So, again, he shouldn't really say this, shouldn't really imply this. And again, the inverse for kinetic energy. Kinetic energy says basically that this destroys energy. Every time you do this, go from the smaller volume at the higher speed to the larger volume at the slower speed, that somehow you've destroyed energy. And then every time you put energy into the slow, higher volume side of the system, you end up making free energy on the other side. So it should just be a slam dunk. We should be all done having a conversation about kinetic energy. It obviously doesn't work in reality. It doesn't make any sense. Hydraulic cylinders do not make free energy. They do not destroy energy. So why for 2 years do I have to every day talk about this subject? Will somebody draw this system and explain how kinetic energy doesn't create the destruction of energy and the creation of energy, depending on what side I put the energy in? Will somebody do us the favor of showing how this drawing of the fact that this is clearly a momentum converter, how that means we have free energy? Because we can convert momentums. And if we convert momentums one way, from big things to small things, we get free energy. And when we convert from small things to big things, we destroy energy.
The other example you need to know about is simple levers.
So he shouldn't have moved to levers without finishing this by saying, oh, wait a minute, we're not making free energy, by the way. But he doesn't.
So here we have a very simple lever. It's just a ruler, a meter ruler, pivoted about a point here. Okay, and at one end is my hand pressing down, at the other end is a big heavy weight, something that I'm trying to hold with my finger. Now this, to solve, we would be looking at using moments to solve this. So we'd be
So this is, I think, a slang of his own. I haven't really heard anybody else use the term moments. Okay, um, they usually say more words to describe a moment as something like an angular momentum moment or something, some other context. But anyway, so we have the same exact circumstances I've been describing with levers, except he's moving the fulcrum instead of the extending the lever. So I'd say there's a flaw in his diagram just because he isn't accounting for the weight differential he has in the lever itself, and it does make a difference. So this really wouldn't come out the way he's saying because he hasn't accounted for the weight of the lever. But whatever.
looking at the clockwise moment and the anti-clockwise moment. Now, let's say I can push down with a force of... Let's say I push down with a force of, I don't know, 20 newtons.
So he's just describing a weight. So, I guess we convert a newton into a pound, and so there'd be 2.5 pounds or some kind of, whatever it is, per 1,000 newtons or 10 newtons. 10 newtons, yeah, something like that. So it's not, this jargon isn't very useful in terms of explaining something that's more human relevant. So they should just say it. He's going to apply a weight, period. And so that'll be a force over a period of time.
What weight could I support over here with that force of 20 newtons? Well, very quickly, anti-clockwise moment is the...
So he's thinking of it in terms of moments being motions in a direction, okay, on a circle. So he's calling it anti-clockwise. I don't know if that's very useful, frankly, but whatever. Doesn't really matter. It has nothing to do with angular momentum beyond pointing out that the guy's basically saying it's just momentum. So angular momentum is just momentum. It's not some kind of special thing.
My finger is causing an anti-clockwise moment. The moment is going to be 20 newtons times 80 centimeters, which is 2 times 8 is 16. Add 2 zeros. Newton centimeters. Anti-clockwise. The clockwise moment, let's call it W, the weight of this heavy thing, is going to be W times 20 centimeters. So therefore, if these two moments are equal, the clockwise and the anti-clockwise, because this thing is in equilibrium, it's balanced, then 20W equals 1600. So W equals 1600 divided by 20.
Right. So he's just doing a ratio, and so he's just splitting this as one thing has 80%, this one has 20%, and they're balanced by the fact that he's brought the weight to equilibrium. He's not really talking about how he's moving the weight of velocity. He's really just talking about the fact that he's balancing the weight. I mean, he's brought it up to the same level as his finger, you could argue, and that's what he's really calculating here. But again, he's calculating it without considering the weight that already is helping move the object, because you have more weight on this side of the lever than this side of the lever technically. So even without the weight, you would have to apply a pressure in the opposite direction to lift the lever. So the numbers are being biased by an aiding lever. So this was sort of the problem with some of the Ian Gosling videos, is that he doesn't have a balanced lever, and he's not accounting for the fact that from the lever's perspective, the weight over here will see the finger plus the weight of the lever. It's not going to just see the finger itself.
Which looks to me like 80 newtons. So with a 20 newton force in,
so he's again going to say he can create an 80 newton force out, and no, you're not really doing that. It's not, you haven't changed the force any, and you haven't changed the momentum any.
Can support a weight. of 80 newtons. And actually, this was a slightly unfortunate choice of numbers because it's turned out to be the same, but there we have it. You'll notice that the ratio 20 to 80 of the forces is in this case exactly the same, because it's actually the same numbers as the ratio of the distances, but this always holds. So as before, where the ratio of the areas tells you the ratio of the forces, now the ratio of the distances from the pivot gives you the ratio of the forces.
Right, and it's all just perfectly proportional. So again, if you put the two weights in the same distance on a balanced lever, then it balances. You move one of the weights twice the distance, then it's deciding twice the amount of weight on one side that's on the other side. If you half the mass, then you go back to evening the momentum again. So it's a momentum converter, nothing more. Doesn't multiply anything.
Except that it's the other way around. Okay, so before, the input area to the output area gave you the input force to the output force, but now you'll just notice that the ratio of the input distance from the pivot was 80 centimeters to 20 centimeters was the output distance, but the force ratio is the opposite way around. I put in 20 newtons, I got 80 newtons out. So you just be
again, so it's just backwards from the kinetic energy disproportion, so it really doesn't have anything to do with that. It just has to do with he's not finishing this math by recognizing the fact that the motion of this object, versus this object is going to be very different, because this has to have a much higher velocity than this side will have in terms of achieving the balance.
Aware that it's the other way around for levers. The ratio is the same, but it's flipped the other way around. So if you are 8 times if your input force is 4 times further away from the pivot, then your force will be 4 times bigger. Now,
so it isn't. So again, he said your effort and your force, these are the same thing. The effort is a force. You can't multiply your energy. You can't multiply the force. You can't multiply your effort. It's all the same.
Now this does the same force multiplication thing as the hydraulic system. If I double my input force here to 40 newtons, I'll be able to support double the weight at the other side. So the ratio of 1 to 4 of 4 times will still...
So it doesn't work. You can't double the weight. You can't double... That's real momentum. You can't double the momentum. So again, his words here are really way off. This is really, this is poor verbiage. I don't know how, it's not very scientific because it's not accurate, frankly. You're not multiplying a force.
Hold. So this will always multiply my input force by a factor of 4. Of course, if I move the pivot, then my force multiplication will change. If I move the pivot...
So again, he's talking about moving the pivot, the fulcrum, right? But it's a very broken idea in the sense that these rules do not apply. He should have said ahead of time, well, I'm going to pretend this lever doesn't weigh anything, because moving the pivot won't fix this imbalance in the weights you have on the either side of the fulcrum, because of the fact that your lever isn't the same amount on each side of the fulcrum.
But now, so it's over. Whoops, sorry. So it's now over here. Okay, and now let's say we've got 10 centimeters here and 90 centimeters here. Now my ratio is going to be 10 to 90, which is 1 to 9. So I'm 9 times further away from the pivot. Therefore, my force is going to be multiplied by a factor of 9. So my force multiplication has changed. So the reason they're called force multipliers...
Well, they shouldn't be, and I don't know who calls them that, and that's really bad jargon. They should just simply be called momentum converters. That's what they clearly do. That's clearly what your math is saying. So why are you calling them force multipliers? They're just momentum converters.
Is that for a given...
And, the very idea of calling them force multipliers when he just does the experiment in the inverse and their force, what? destroyers, unmultipliers. What are you going to call them then when the multiplication is in the negative direction? What do you call them then? Force decliners, force suppressors? I mean, come on. It's really bad jargon.
Setup for a given pair of piston sizes or for a given pair of distances from a pivot, the machine multiplies the force by a set amount. Now, if you're worried that this force multiplication is occurring and it seems like we're getting something for free, we're not.
Yeah, so then why are you saying it? I mean, I'm just saying, you spent the whole video basically implying it, saying it. We're multiplying the force, we're increasing the force, we're making more force. And anybody, I think, rational equates force to energy as some proportionality. I mean, I'm overtly telling you it's the same thing as energy, but whatever. It certainly has a connection to it, and you're implying the creation of some sort of extra free energy, and it's just a really stupid implication because it's unnecessary if you just convert this force multiplier to momentum converter, because that's all it's doing. It's converting 1 MV into a equal but different MV.
Okay, so force multipliers multiply force by a constant factor, but they divide distance by the same factor.
So again, this obsession with distances when, you know, the forces act over time, but whatever. So now he's just saying the volume in the case of the hydraulics is now going to be his measure of distance. Distance is related to volume, and then in the lever it's going to be velocity. It's going to be related to distance moved.
Which means that the product of force and distance remains the same. So you may or may not remember that work done equals force times distance.
Can you see that? I'm just curious. He writes way up on the top. Yeah, okay. So obviously that's just a silly statement. I mean, the work is the momentum, frankly. It's the force. It's all the same thing. And the force is a weight, and a weight is applied for an amount of time, and that dictates how much force there is.
Okay, work done meaning energy transferred. Well, if we multiply the force by a factor of 4, it turns out we divide the distance by a factor of 4, meaning that the amount of work.
And so again, in the case of the lever, the distance is only relevant because of the fact that it has to happen in the same amount of time, because it's a rigid lever, so it really is just a velocity. But whatever. It's just the wrong way to think of how force is applied. Force isn't applied over a distance, it's applied over an amount of time.
Done is the same on each side. The energy transferred is the same. We're not getting more energy out. How does this?
So he's saying there's no more energy out, so he should be just saying you have the same momentum. So if you've converted the momentum, you've taken a little m and a big V, and you've converted into a big M and a small v, and you have the same amount of total weight.
This occur? Well, it turns out it's quite intuitive. So if you imagine this situation here with our pistons, and the piston's right at the top here, the plunger is right at the top, and we move it down a distance of, let's say, 5 centimeters, that's going to displace this whole volume of fluid here. That whole volume of fluid here there has to go somewhere. Let's say the piston here is in this position at the moment, so it's got some space to go up. Now, when that fluid travels through the system and goes into the other piston, obviously it's going to spread out more because this piston has got a much larger area. So the same volume.
So he didn't, well, he didn't use the lever as an example, but I guess you could still try to convert it into a distance argument when really you're just basically saying you're going to move this fluid a lot faster than you're going to move this fluid. The atoms are going to move faster here than they're going to move here because of the amount of distance over which you're filling the space. So they're a lot It's going to take you a lot longer to equalize the pressure here to here. Let's see how else to say it. It doesn't matter. I mean, the point is made either way. I just wouldn't bother measuring it by distance. I would measure it by velocity.
The fluid is going to make that piston go up by a much smaller amount. How much is it going to go up? Well, if we really want to, we can work out the volume here. So we've displaced 50 centimeters squared of liquid here. Since liquid's incompressible, we must also have displaced 50 centimeters. Sorry, did I just say squared? Cubed, my apologies. 50 centimeters cubed of liquid there. Therefore, we must also have gained 50 centimeters cubed of liquid here. Well, if the area is 50 centimeters squared, then it's only moved up by 1 centimeter. So even though this multiplies our force by a factor of 5, it divides the distance it moves by a factor of 5. So it only moves.
So whatever. Again, it's not. That has nothing to do with the force. You didn't put more force in. So force is the final number. Okay, it's not the. Force isn't mass, and force isn't velocity. Force is a combination of mass and velocity.
A fifth as far. So that's the trade-off. You get more force, but the distance is less. So you have to move your input through a much greater distance than the output moves, which conserves energy.
So I'm just saying, if this, look, if we just said is true, then you're stuck with the kinetic energy theory and trying to make any sense out of it, but you can't. Because you're basically saying every time I put a force in this side, I'm going to get less energy out the other side. And every time I put force in this side, I'm going to get more energy out of the other side. So if what he just described actually happens here, where there isn't this 1.4 thing that Brozo says happened, right? So I put the energy in this side. I put one quantity of energy in this side, pressure. And I only get 1.4 out the other side. I mean, that's his theory. Velocity. So the component I put in this side, I only putting in 1.4. Somehow I put in 1, and I'm going to get 1.4, even though this one, say, was half the size. So I should have said that first. Let's say this is twice as big as this, which it actually looks like, right? So it actually looks like 2 to 1 instead of 5 to 1. So the simple analogy is that I put a force in this side, and somehow I'm going to get twice the momentum out the other side. But what I'm going to get is twice the velocity. And if I square the velocity term, obviously you can understand that now I have twice the energy on this side. All right. But Brozo says it doesn't work. It doesn't convert momentum. It converts kinetic energy. So for the kinetic energies to match, this has to only increase, instead of increasing by 2, that is, it goes twice as fast because it's half as heavy or half as much volume. He says it only increases by 1.4. And he says he's proven that with experiments. I'm just saying, well, that's obviously garbage. That didn't happen.
The same applies to the lever. I'm sure you can imagine, without doing the calculations on this, that when you've got a lever set up like this with the pivot off center, then
yes, well, why put it off center is the simple statement. Okay, why don't you just put it in the center, eliminate the stick as being part of the math that you're supposed to do, and then do the experiment by distance. You can still poke this side at 80 centimeters, and you can have 100 centimeters on both sides, and you still poke one side at 80 and one side at 20 and do the math. But at least you'd be getting right answers instead of fake answers, because you would account for the fact that the lever's been negated because you have the same amount of lever on both sides of the fulcrum. But in this case you don't, so your answers aren't really accurate.
If you move this end of the pivot down by a certain distance, this end is going to move up by less. It's not going to move up the same distance because that end is much shorter. And indeed, as before, if this is multiplying the force by a factor of 4, then the distance it moves will be divided by 4. So you probably...
And again, it has to move that distance in the same time, obviously. This end and this end will be moving those distances in the same time. So that means that this is 4 times the speed. So kind of simple.
Won't be asked questions on that necessarily. I mean, they could do. I haven't seen one, but it's mostly just to make you realize that you're not getting anything for free here.
Right, you're not getting anything for free unless you believe in kinetic energy. So if you believe in kinetic energy, you are getting something for free every time you go from heavy side to light side. Every time you increase the velocity, you increase the energy. And just a fact. And 2 years of having to explain this to what are supposed to be intelligent people, this is paradoxical. You cannot say this happens, okay? You can't say this lever thing happens and then argue that kinetic energy is completely compatible. The theory of kinetic energy is completely compatible with these facts. It's completely incompatible with these facts. It doesn't happen in the real world. I will not create free energy by pushing on this cylinder and watching this cylinder pop up with twice the energy or 5 times the energy or 50 times the energy or 1,000 times the energy. It won't happen. Okay? It will do exactly what is predicted. It will move these extra velocities. A bullet will come out of the gun a hell of a lot faster. All right, but it won't come out of the gun with more energy than the recoil of the gun.
Energy is being conserved, and the trade-off you get...
So again, energy is being conserved, not kinetic energy. It's no conservation of kinetic energy, so it's just a big lie to say energy is conserved. Oh, I mean energy, in the momentum sense. So, I mean, this is this is just such junk as physics. So this is their science. They got a gigantic paradox sitting right here in the beginning. They can't define energy correctly. If you say physics is about something, if I showed you the cover on physics books, right? The covers are all about energy, things blowing up, sparks, stuff moving. They always try to put movement into the images, right? The images always look like they're things that are moving. Energy is fundamental to understanding physics, and here they have a gigantic paradox right in the middle of their physics, and they just don't care. They just use this word jargon to evade what just doesn't make any sense.
The multiplying force is by losing distance travelled. Hope that's been helpful and clears up what force multipliers are.
So again, this is what they're teaching, and it's just junk. So there isn't much here. Excellent, thanks, great. I found the reason I was searching for. Obviously, and then some snarky troll has to say, you're watching this because the teacher told you to. Like, nobody could be interested in physics. Yeah, sure. Okay. You're a jerk. All right.
How they work.
So that's it. Terrible, really. I mean, it clearly illustrates my point, right? There's no, he clearly didn't use the word kinetic energy. He clearly didn't get anywhere near it because he knows if he starts talking about kinetic energy in those two circumstances, it's not going to make any sense at all. All right, so let's see what else we can look at because I believe there's still no comments. Well, let's go look and just see if there's anything, if anybody's here. So that would help, just to know. 8. Oh, okay, well, that isn't completely horrible. Yeah, okay. So, let's see if anybody has anything to say eventually. I'm just saying, it's, it'd be nice if you just said, yep, that pretty much does it. I mean, I'm convinced. How do you explain levers? How do you explain hydraulics in terms of kinetic energy theory? It's clear he just argued that you do conserve the momentum. No doubt about it. Momentum is conserved. The outcome conserves the momentum. And it's clear that if you conserve the momentum and you converted the momentum, that is, you successfully converted from a fast thing going slow, a fast thing, the light fast thing to a heavy slow thing. If you successfully did that, you just destroyed a bunch of energy, and if you went from the heavy slow thing to the light fast thing, you just made buckets and buckets of free energy. That's the truth. It's right in your face. Please explain. Okay, anybody who thinks I'm a science denier, explain where I went wrong and I didn't understand what he just asserted clearly. He told Ian and Brozo, you are wrong. Okay, kinetic energy is not conserved. Momentum is in fact conserved, and levers are, by your theory, free energy devices. There's just no doubt about it. They will make free energy, free kinetic energy. So explain where I have made an error in pointing out the actual facts. Okay. Alright, so let's see if we can find another one that's on... Oh, God, this one I wanted to see. Okay, so I haven't seen this one yet, so we'll watch this one. This one's more overtly described as conservation of momentum recoil. So this is the gun and the bullet. Something
Right,
like
I
that.
thought I'd show you a quick demonstration I've just set up. I'm not sure if it's going to work or not, but the idea is to show an explosion and conservation of momentum during that explosion. Now, I haven't got anything set up to actually measure if momentum is conserved, but the idea is just to see this in principle. So, what we've got here is, firstly, a trolley, which is pretty much free to move. There's quite a small amount of friction.
Quite a lot of friction, frankly. Okay, it barely came back, so yeah, but who cares?
So it approximates to being a closed system where there's no external resultant force acting. So momentum should be conserved just with this trolley on its own. If I push it and give it a certain amount of momentum...
Yes, it conserves it for a certain amount of time, which isn't very long, but it's... Who cares? Because it's long enough. Alright, so it conserves the momentum, but it only conserves it for a very short time, and then it slowly leaks all the momentum.
In an ideal world, it would continue with the same amount of momentum forever and ever and ever, which on this runway it would not, but it's reasonably close. The other component is a gun I've just made out of an elastic band on a piece of wood, and the thing it's going to shoot is a weight, which is quite heavy.
Alright, so in one of his other videos that I may get around to playing, he actually points out that elastic bands don't follow Hooke's law very well. That they're pretty bad in the beginning and pretty bad at the end. So they only have a tiny portion that's consistent. And that springs themselves really only work in the 80 in the middle. When you're starting to really stress the spring in terms of compressing it, it's not too good. And when you're expanding it, likewise, not so good. And when you initiate the action, the initial action isn't too good either. So that's something to be appreciated for people like Brozo who think they can compress springs any amount, and it just doesn't matter.
Now, it turns out the weight is almost the same mass as the trolley. The trolley's got the bit of wood on it which adds to it, so the masses aren't exactly equal, but it doesn't matter. Momentum should be conserved whether the masses of the two objects are equal or not. So, what's going to happen here? Well,
what's going to happen is an explosion, and they should describe it as exactly what he said. He says it's an explosion. Well, explosions go this way and they go that way. Alright, there's no positive and negative direction. There's energy going one way and energy going the other way. So, I've sort of tried to say that Newton's third law is sort of being misunderstood because it keeps talking about an opposing or opposite force, and frankly, the two circumstances that really create all the interactions really just have to do with something expanding or contracting its size, that is, pushing in all directions, okay, or pushing in all directions, either expanding or contracting, which is the explosion, or it's a circumstance where one object has motion and it gives it away to another object. By giving it away, it looks like it's now gone in the negative direction. but it's not really because of some new force. The very act of giving away what it has means that it has less, and the other thing has more. There was no equal and opposite reaction. There was just the one action of one object giving away what it has.
Let's get that bit of string out of the way. The gun is going to fire the weight off to the left. And if the weight fires off to the left and nothing else happens, then that looks like momentum is being created, because before this event happens, there's currently zero momentum, total momentum before.
So we know that the total momentum before is just like saying gravity is zero momentum or something. There's no non-momentum. We know we set up a circumstance that's got plenty of momentum and plenty of force. Force is momentum. So now we're going to apply the force. And by applying the force, these objects are going to share, okay, in that explosion. And depending on how you set it up, whether you're actually going to force the explosion to move, you know, like a collision, you can have two cars hit each other, and if they have equal momentums, the crash doesn't move anywhere. If they have unequal momentums, then whatever one has the greater mass will end up pushing the moving the collision.
If the weight goes shooting off to the left, then we've just created momentum, which is not allowed, because we've just said that this is a closed system with no external resultant forces acting.
So, I mean, it just doesn't, you know, it doesn't really mean anything to say, well, if I put my hand on this object and just shoot this object, that I created momentum. You didn't really create it, because, you know, you have a mechanism that's causing it.
So, the weight can't just fly off to the left. Something must move to the right to cancel that out. You remember that momentum is a vector, so if we say...
So the argument is that it really doesn't have to move. I mean, in a real sense, in the sense that the Earth isn't going to move. So if I tie it to the Earth, okay, the idea that the Earth is going to move in some way we could calculate would be kind of ludicrous. But the fact is it will move in ways that we can't understand mathematically exist. I guess you could argue it that way. So yes, it's going to be disconnected. One object's going to remain connected to the Earth if we nailed it to the floor, and the Earth will move relative to the atmosphere.
Moving to the right is positive and moving to the left is negative. Then it's entirely possible for these things to both start moving, and yet the total momentum afterwards be zero, because one has positive.
So there's no point in saying total momentum is zero, because you have two objects with momentum, so why say that? I mean, really. You have two objects flying into the universe's space with velocity. It's kind of stupid to say they don't have momentum. Of course they do. They're moving. Eesh.
Momentum, and one has negative momentum. So that's what we're expecting to see. We're expecting to see the...
I mean, the whole relativity thing does make a mess out of it, but I'm just saying it, you know, we can all understand that the change in the momentum will be significant for both objects. Both objects are going to have a change in their momentum. And the change doesn't equal zero. The change equals something relative to their current conditions. One's going to go left and one's going to go right. And if one's already going left, then it's going to go faster. And if one's already going right, it's going to go faster.
Trolley move off to the right with positive momentum. The weight move off to the left with negative momentum. And for the total momentum to be zero, which is what it is at the start. Now look, it's probably, you know, we can't measure whether it's zero or not, but we can get a rough idea just by having a look at it. So what I'm going to do is try not to exert any external resultant forces by pushing it or pulling it or doing anything. So the way I'm going to try and release the string is by lighting a match and burning through it, so I don't actually really come into contact with the string at all. No idea.
Right, so this is all part of the show, is this idea of, I don't know, even if burning something is exactly the best way to disconnect it, you know, benignly. I mean, maybe a sharp razor blade would do just as well or better, but whatever.
If this is going to work, but we'll give it a crack. Now, is momentum going to be conserved? Is the weight going to fly that way and the trolley fly this way at roughly the same speed?
Well, why would it be, unless they're the same weight, there wouldn't be roughly the same speed. So I guess he's saying this weight on this wooden thing adds up to the weight of the cart and the wooden thing.
Let's find out. So I'm going to try not to touch the setup at all.
So just, emphasizing that, yes, quick releases are really important because there's a lot of very fast motion that's going to take place. And you can mess up that very fast motion with your very slow fingers. And so the idea is to have some release mechanism that allows the energy to move at its maximum speed, which it will do at initiation. So the maximum pressure is at the very, very beginning. So it's the most important part of the experiment, because that's when most of the energy will be transferred, is in the very beginning.
Don't exert any force on it. I'm just...
I guess he should have had a cart for this thing to land on, and then he could have left at the same speed, but obviously because of friction, this didn't go very fast. Somehow there was a lot of friction here. It didn't go very fast, didn't go very far. So again, this whole work equals distance thing, there's no work here. But obviously there was a lot of work, a lot of friction absorbed a lot of energy.
There we go. Can't wait to see that one replayed. It certainly looked to me like the weight got fired that way and the trolley went this way. Now what we call, with guns and cannons and all sorts of things like that, these sorts of explosions, we call that recoil. When something shoots one thing one way and then the thing that's shooting it moves the other way, we call that recoil. And that occurs when anything like that happens, when any cannon fires a cannonball. If the ball flies off one way, then the cannon at least is going to try and fly off the other way.
And he's not really pointing out by Newton's third law, they basically have to conserve the momentum, so the cannon will have as much energy as the cannonball, it just will be in a different form. But Newton's laws were written before kinetic energy was invented. So, does Newton's law apply to kinetic energy? No. They can just they can have as much extra energy go in the other direction. So if I use this analogy and just compare it to a gun, the fact is that it basically is telling me that the gun goes off at 2 joules of energy and the bullet leaves with 2,000. It's 1,000 times difference. It's actually, real guns are more than that, I think. 1,500, 2,000. I mean, it's an insane disproportion.
Although there might be some resistive forces slowing it down so it doesn't go on forever, which would be not very advantageous. Why does all this happen anyway? Why is momentum conserved in the first place? It all comes down to Newton's third law.
So I don't know why it has to come down to Newton's law. Why doesn't it come down to a pile of logic that says, well, mass, you can't create it or destroy it, and velocity, you can't really create it and destroy it. So all you have are those two components. They define the momentum. Of course, there has to be conservation of momentum because there's no way to create movement. Okay, the Descartesian notion that it just moves from one thing to another thing, and we clearly see that. The scale doesn't move until something applies a force to it. We see it all over the place. It's kind of obvious. So why is there any confusion at all? It makes perfectly good sense that you have to conserve the motion because you have to conserve its origin. Okay, there's no place to create it for free.
Which says if one object pushes on another object, then that object pushes back with an equal and opposite force. And
so there's no pushing back in the sense that there really isn't. Okay, it's an explosion type thing. Again, they're pushing in both directions. So in the gun, there's no pushing back. Nothing's pushing back. You're actually pushing a bullet this way, and you're pushing the gun that way, and there's no pushing back.
Sort of what's going on here. So when this object here, the gun, pushed on the weight in this direction, forces can't exist on their own in isolation. So Newton's third law says forces always come in pairs. They have to. So
all right, they really don't come in pairs, so it's just kind of baby talk. to say they come in pairs, because I can do the same thing with a collision of cars, and one's already moving and it's going to bang into one that's not moving. There's not going to be any counter force in the opposite direction. There's just going to be forces moving this way. One's going to share its force with the other if the one that's hitting weighs more than the other one that it's not hitting, that's getting hit. And so it's stupid to say there's an opposite reaction. There's just one object giving its energy, a portion of it, to the other object, and when it gives a portion of its energy away, it moves slower, but there's no counter force. So it's just wrong. It's a wrong way to say it.
If the gun is exerting a force this way on the weight, then the weight must be exerting a force that way.
So the weight doesn't exert any force at all. The gun, the cart is just simply experiencing the other half. Okay, the rubber band has to be thought of as just being in space. It's contracting. As it contracts, it's pushing on one end of the rubber band, the other end is pushing, and the two pushes are in the opposite direction, and that's all you have
On the gun, and therefore on the whole trolley thing.
And clearly it's just pushes. There's nothing's getting pulled anywhere
because they're connected together. So if a force is being exerted by the gun on the weight is exerting a force on the gun. And as
Alright, so again, he's basically just saying conservation of momentum. Every time there's a video that says conservation of momentum, you have to recognize that that's a free energy theory by kinetic energy. So every time we conserve the momentum and we change the mass to velocity ratio, which we did in this case, we have two different things. He says they're close to the same mass, but who knows. Alright, so by kinetic energy you wouldn't create any free energy problem if the two masses are the same. The cart and the wood equals the weight. Because you're just lucky, because the squared term isn't going to matter now. Because you're squaring the same amount of velocity on both sides. But every time I do this example like a gun, where I have a big heavy gun, 1,000 times more atoms, and a very small bullet, every time I do that example, I will be making free energy in one direction.
we've seen, it's a very low friction situation, so if force is applied by the weight on the gun, then the gun moves that way, and the weight accelerates this way. So it's all down to Newton's third law. I hope that's a half-decent demonstration anyway, because I couldn't really find any.
So yeah, and you could also just say that the friction, though, of sliding the two things against each other probably isn't too good, so you lost some percentage, 20% or whatever, in heat you created, because you didn't really create a frictionless surface to slide it across.
On YouTube. Obviously the whole calculation.
So he didn't find it on YouTube 8 years ago, and yes, there's still not very good videos on YouTube. And that's really sad, considering it's physics, kind of an important subject.
Calculations thing is a separate thing, which I'll do in another video, or link to one. But I just wanted to give you an actual demonstration of it in action.
So there's a third example of all I do is change the weights of the two objects, make them two different weighted objects, and I will either destroy or create energy by the kinetic energy formula. So completely fails another test. No point in saying conservation of momentum. You don't think momentum is anything that matters, so why bother even saying it? Because frankly you don't believe in it, because obviously it would be a free energy formula by kinetic energy, so you have to either believe in one or the other. There's no point in talking about conservation of momentum in that example. So he has crumple zones here, which I don't think that's worth playing, but we'll see. If nobody shows up, then we'll might out of desperation play with that. So here's one on gears, so I guess we could do, so this is another example where it will conserve momentum. Okay, but if you did the calculations for kinetic energy, you're making free energy. Alright, so moments. So this is his term. Again, I think it's just kind of, it's not very scientific. You know.
Okay, I'm just going to give you a bit of recap.
Have to bring the volume up.
Since you haven't done this since at some point in GCSE. So here's a GCSE question where you've got a 300 Newton force on a pedal in 3 different positions, and the question is which position does the force have the greatest turning effect? In order to answer it, you need to know the perpendicular distance in each case, since moment equals force times perpendicular distance. So if you've got it, GCSE, I'll show you the technique that I use for my GCSE students. So,
all right, so I don't think theoretically there can be any difference, right? So, if this was a gravity, if you was going to use gravity as part of the equation, well, then you'd understand that you're going to be aided by gravity going down a lot more than you're aided by gravity going sideways. So as you're applying the force in the sideways direction, you're not going to be aided by gravity much, but in the downward direction you are, so there would be some unevenness in the application of force just by the fact that gravity is going to help you more in one part of the cycle than it's going to help you in the other part of the cycle. But I don't think he's going to do that.
So step 1, extend the line of action of the force. So go along the force, the line of the force, and extend it in both directions.
All right, I see what he's doing. Okay, so this is applicable to the experiments that Brozo and Ion have done, in the sense that they don't appreciate that, yes, if the force is in line with your lever, then all you're doing is putting friction on the bearing, and there's no real turning potential. And it's not until you're in balance, the force to one side or the other, that you start adding that force by this angle. And the more perpendicular the angle, the more 100% of the force is in the action of moving, where instead of pushing on the fulcrum. So all they're doing in this case, if there was a lever and you put a weight on a lever, all the weight is going to be doing is pushing on the bearing. It's not going to be turning the wheel. So this is probably kind of complicated math, but let's just see.
Dotted line. There's the line of action of the force.
It's going to have a sign to an angle in it.
You want to draw a line from the pivot to the line of action so that it meets it at right angles. So if I go from the pivot here to the line of action, okay, I want that line that I've just drawn to meet the line of action at right angles. Now this one has not met it at right angles, so that is not the perpendicular distance. Okay, let's get rid of that. This line here does meet it at right angles. That is the perpendicular distance. So this would be the perpendicular distance D, goes from the pivot to the line of action of the force and meets it at right angles. In this,
so you're really just finding some way to measure, mathematically understand, the percentage of the circle, this argument that when you're going across the top, you're doing a lot of this way motion and very little down, and when you're going on the side, you're doing all down and you're doing very little side to side. And so that's how much of the force we'll get to the turning action is based on what angle you're at, because that increases the amount in the right direction.
Situation, the line of action goes right through the pivot, so the perpendicular distance is just 0. And in this case, I'll go from the pivot to the line of action of the force and meet it at 90 degrees. That's my perpendicular distance, D. Now, this is A-level, so you need to be able to go a bit further and not only identify where D is, but calculate what it is. For us, this is pretty simple. In all 3 cases, it turns out. In C, we know what D is because they tell us it's 16 centimeters. In B, we know what D is because we just worked out it's 0. But in A, we're not immediately sure what D is, so we've got to use some other technique to calculate it. Now, if I just redraw it over here, we've got our D here. We do know from another diagram that the length of the crank arm is 16 centimeters. And they've told us that this distance here is 14 centimeters. Now that distance is not the perpendicular distance, but it's useful for us because we've then got a right angled triangle with D 16 centimeters and 14 centimeters, and you would be expected at A levels certainly to be able to deduce D from that using Pythagoras. You might want to check that now and calculate what you think D is.
So it'd be the square of 14, the square of 16, give you the square of D. Okay, and then you just do the square root.
That you would then put into your, 300 newtons times D to get your moment. I think I did it a minute ago, and it was 7.7 centimeters, the perpendicular distance. But check that. You might also have situations where...
Alright, so this isn't, like I said, we don't need this because it's sort of a different subject. Well, it's not that different, but it is different. It's all part of understanding. I mean, this is basically a lever, and understanding that the lever doesn't work as a balance when it's not perpendicular to the forces you're applying. So unless your lever is perpendicular, any off of perpendicular, substantial off of perpendicular, is going to start degrading how much force is actually going into the lever, and how much force is going to be wasted as just pressure on the fulcrum. So in the balance condition, the fulcrum is almost irrelevant, and in anything other angles of pitch are going to mean that more friction goes into the bearing. Okay, I think that's the reasonable conclusion. Alright, so let's see what else we got. This is wave stuff. We did force multipliers. Bad video. MGH. Let's do that one. Because that's inherently wrong answers, frankly. I mean, MGH is going to give you the wrong answer because it's not appreciating the simple Galilean principle that 4 times the height is only twice the velocity. You're only doubling the energy or force.
Okay, just continuing with the BMAT physics questions, up to question 16 now, where we've got to compare what's going on when a switch is opened and a switch is closed. So,
wow, that was weird.
Different approaches to this. Obviously you don't have to follow my approach. I suppose I'm going to show you an approach that's consistent with the last approach I used before.
Let's get to the...
What do you need in order to create a potential difference? You need blah 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 blah.
Primary coil. Alright. So it doesn't have energy.
V is now
H
0.
After all.
So all of its kinetic energy has been transferred into gravitational potential energy.
Okay, here we go.
Conservation of energy viewpoint. Okay, so think about, it's the opposite of what was going on before with the thing being dropped. Now it's got kinetic energy, so the water's being shot upwards with V. Okay, and when it gets to its highest point, V is now 0. So all of its kinetic energy has been transferred into gravitational potential energy. Okay, so half mv squared is going to equal mgh.
Right, and so that's true, but obviously that isn't true in the sense that that's not real energy. So that's just fake energy, because the real energy is going to be just half of that in terms of, depending on what numbers you're using. Let's see how to best say that. I mean, this is obviously this stupid force multiplier, so the more velocity you put in, the higher you'll end up going, and it's always going to be at this 1 to 4 relationship. So let's see how to say it. Just a wrong answer, frankly. It's fake energy. They're not real joules. It's not real capacity to do any work in the universe. None of that'll happen. When the water falls this distance, it won't have 4 times water at half the velocity. So what they claim to be true won't be true. It won't take 4 times more fuel to go twice as fast, put simply.
Okay, that should allow you, since you know the m's cancel, since you know g And since you know h, because I think it...
Alright, so we know h, we could just as well know the time. We know that it's going to go, if I drop it from 4 times the height, it's only in gravity twice as long. Gravity is a time-dependent force, 9.8 meters per second on Earth. It's per second that you gain the 9.8. So in 1 second you gain 9.8. In the second you gain 9.8. The fact is, when you drop from 4 times the distance, it only takes twice the time. Okay, so, you know, it's clearly, again, this is just failure. This is a failure to accurately describe the reality. The reality is that gravity is time dependent. You acquire the force based on how long you're free falling in the gravity. The distance is not revealing in terms of showing you, because the fact is, in the first moment, the first half of your voyage, okay, in time, you'll travel a very small distance. In the second half of your voyage, you'll travel 3 times the distance. The distance isn't telling you the truth, because in that 3 you're only going to gain the same 9.8 that you gained in the 1 unit of distance. So again, it's just garbage physics. It's not good science. It's really bad crap.
Tells you what it is. You should be able to work out v, the speed at which the water leaves the thing. Okay. Then, if you want to know the power of the pump, I guess you've got to think, how much kinetic energy does it need to give the water in 1 second? Okay, because power is energy per second.
Which doesn't make any sense, right? So all they care about is this h stuff, and now all of a sudden they care about seconds, you know. But they've already ruined it because they've calculated it having more energy than it actually has.
Energy transfer per second. Okay, so I'm imagining that it's taking water that's got no kinetic energy, and the job of the pump is to give it kinetic energy. The question is, how much kinetic energy is it giving the water in 1 second? So
we know that the speed of the water is going to depend partly on the nozzle. So it'll be more pressure if I have a smaller nozzle, and I can shoot the water at a higher velocity. And again, they're going to say that because I am shooting the water at a higher velocity, that somehow I've created free energy. So again, it's another system where they're saying, because I changed the velocity, I changed the energy. When, yes, I changed the velocity, but I very radically reduced the amount of mass the water has. And so I have, you know, the same momentum in the system, whatever the losses are to friction in the nozzle. And you know, but one theory says I'm multiplying the amount of energy in the universe, and the other theory says no, you're just applying the energy in a different form. More mass, less velocity, more velocity, less mass.
you know the formula for kinetic energy.
Garbage, a waste of time, neurons gone bad. Okay, this is just brain killer. You want to kill your brain, you want to turn your brain into garbage. Okay, believe this, because it's garbage. It's useless nonsense. It's a figment. It's a gremlin. This is a fairy or a pixie. Okay, this is a piece of crap. This is a God or a Jesus or a Mohammed. This is just crap. It's religious theory. It has nothing to do with reality. It's a talking fish. It just breaks the narrative. The physics narrative is broken by this rubbish idea. It had no credibility when it was invented. It doesn't have any volume of experimental evidence demonstrating it. All, you know, again, it's more just bad physics. If you don't understand that the shape of an object dictates how fast it penetrates or how well it penetrates another object, then maybe you could fall for this crap, but that's all it's got. Other than that, it has no evidence backing it at all.
No V, because you've just worked it out. I guess you've got to work out M, how much water does it do this to in a second? Okay, so how much water does it have to speed up and give kinetic energy to every second? That's probably what I would do. Okay, this one looks hard. There's probably a number of ways of solving this one as well. Obviously you could solve it with Suvat if you know Suvat, but if you haven't done maths A level you don't know Suvat. So different approaches for that. See how you get on with it. Oh look, and it tells you to take G to be 10 as well, which is why it gives you these nice answers. Okay, lovely. Let's keep moving. What happened there? Went the wrong way.
Alright, well, whatever. Okay, I think that's it for the part that I cared about. So, again, just more example of, the failure of their physics. Alright, Newton's second law of trailers. Now, that's just a pulling force, so that's not... Oh, this double-slitted demonstration was really quite pathetic, so we'll do that. So it was really bad. So I suppose we should start from the beginning, but there's a lot of boring bits.
It's named after a bloke called Young, who did loads of really cool physics. And this.
All right, so I've got to replay that just because it's just so bad. The whole Young interpretation, the math doesn't even work, the analysis doesn't work, the drawing doesn't work.
Okay, so I'm going to try and demonstrate to you a practical experiment called Young's double slits, named after a bloke called Young, who did loads of really cool physics.
All right, so he did lots of, frankly, it's not just physics, but I mean, he was a doctor. He did lots of stuff about how eyes work, color blindness, lots of, other good science. But this was really bad science.
And this experiment uses two slits, as the name suggests. And this is really an amazing experiment, and you've got to do it yourself to really appreciate it. But I want to take you through.
So again, it's amazing in the sense that they confuse you enough that you start thinking crazy things are true, and you start thinking, oh, a photon's going through both slits, and it's, magically turning into a zupaton, and the zupatons are entangled with each other, and then they get to the target and they decide where they're going to hit, and it's all kinds of crap as people believe, and it's just crap.
With this video first. If you're in my class, then you're going to do it next lesson yourself. We've got enough for you to do this experiment in pairs. So what does it involve? It involves this, which is a spirit level that's got a laser in it. So if I point that at the wall there, hopefully you can see it's a red laser. It's a nice low power laser that's going to be safe for us to use. Young did this hundreds of years ago, so he didn't have lasers, but they make our life easier, as you will see.
Right. So he, even worse, he did it in, he didn't use monochromatic light. And so we got a bunch of colored spots blurring over each other. And he clearly didn't see the double slit pattern because he didn't do it well enough to see it.
We've got this thing here, which is a collection of double slits. So if you look really closely, you can probably see 4 slits in this slide. If I hold it up to maybe a white background, you see it more clearly. Each of those things that you can see there.
So these aren't double slits in the sense of Thomas Young's experiment because they're not infinitesimally small. That is, they're not smaller than the wavelength of the light, blah, blah, blah. They're not narrower than. So 0.15 millimeters is the width of these openings. Now, in this one, the line is so small that you might argue that it's getting very close to being small enough at 0.25, but it's still not. Right? Yeah.
Oh no, that's lovely. That's focused really nicely. So you can see that each of those things that looked like one slit is actually a pair of slits. And the ones on the right are quite far apart, and the ones on the left are really close together. So these are double slits. What happens when the light...
So we're talking really about a very narrow impediment put between them. So a little thin, tiny distance between them. So the tiny distance creates the envelope, and the wide distance where the two outside surfaces are going to create the small bars. So the small bars are going to be created by the distance between the two outer surfaces, and the big envelope pattern is going to be created by the little wire in between. Those two surfaces are going to control where that's placed.
Passes through these two slits is that it's...
So again, it's getting very close to wiping out the envelope pattern, but it's still there, and you can see it in the experiment, and he just, he cheats.
spreads out. So when light passes through a narrow gap, it spreads out, it diffracts. And then the light coming from each of those two slits can interfere. So I'm going to shine the laser light through. I'm going to use the leftmost pair of slits because that's going to work best. So I'm going to shine this laser through a double slit, and then all the way over there, I'm not sure if you can see it, is a screen. It's a long way away, and And you'll find out why that is shortly. So here we go. I'm going to turn the lights off. I'm going to turn the laser on, and I'm going to direct the laser through 2 of the slits. So the laser light is going through a double slit, 2 slits very close to each other. All the way down there on the screen, you might just see some red. Now, actually, let me show you what it looks like without the double slit. Without the double slit, it looks like a dot. Okay, let's go back. Now, I've put a double slit in the way. So the laser light is passing through both of those slits, it's spreading out, it's diffracting. But when it gets over here...
So I suppose there's nothing wrong with saying it's diffracting, but the real truth is it's scattering off the surfaces. And so you do have the real pattern here. You can sort of see it in the blur that this is 3 nodes here, and you know it's always an odd number. So the center is made out of 3 nodes, and that means these side ones are going to be 2. Because the center is really just made out of 2 of these, this I guess what we call the node. And these are 2 here, but one of them's getting very dim because it's further out. So it's 2, 2, 2, it's 2, and then 4 in the center, and the 4 is made because the 2 are overlapping, and that's why this one in the middle is bigger, is because essentially you're overlapping 2 2s. Alright, and what you really clearly see is that you have a big break here. Okay, it's not the break that's here, it's a bigger break. Okay, and it should be sort of almost the size of a node technically, but obviously the darks are always much smaller than the lights, and in this case the lights are 80% and the darks are like 20 or even worse. So obviously this dark is huge compared to these little tiny darks that are in between inside the nodes. You don't even see them here. You don't even see any separation. The dark separations are so small.
You get this.
But it's clearly a group of 3, then a dead spot, then a group of 2, and then a dead spot, and then a group of 2, and a dead spot. Well, you can really see it here. 2, 2, 2, yeah.
Very interesting pattern of bright and dark fringes. So it goes bright, then dark, then bright, then dark, then bright, then dark, and so on.
So he's going to draw this as if these darks don't exist. So he's going to forget the envelope. So again, the envelope's getting near death because you're down to 3 because you've got a really tiny wire. So the wider your separation between, you know, the middle impediment, the wider you make it, the more nodes you're going to be having inside the envelope. And the smaller you make it proportional to the outside dimension, the less nodes. So. But it's clearly not a single slit pattern. This is clearly a double slit pattern. This isn't what Young drew. This isn't what Young analyzed. Young analyzed a single slit pattern and called it a double slit pattern.
So this is a 2-slit interference pattern of light. Now, if you're in my class, we've already done this with other things. We've done this with sound. So we had 2 sources of sound.
So again, they do this with water, and they pretend that all waves are the same, and they're all created by the same mechanism. Water is different than sound. Sound is different than light. It's just all silly. This is not a wave phenomenon. This is not interference. This is caused by scatter. You're taking photons and scattering their phase. The surfaces are breaking their phase. Breaking their direction is the same as breaking their phase. So when it scatters the light into all kinds of directions, it's changing its landing phase, and there's a 50-50 chance that when you take all the pieces of light that you change the phase of, that they're going to be going in phase or going out of phase. So you're basically just saying, yes, I'll take all these pieces, I'll throw them against a similar surface, and there's a 50-50 chance I'm going to reconstruct a photon.
Same frequency, playing the same pitch, and we walked past them and we noticed that in some places the sound was loud and in some places it was really quiet. I also tried to demonstrate...
So this is obviously not as simple as that. There's places that are louder and softer, and there's all kinds of nuance here. There's these big dead spots, big dead spot, big dead spot, big dead spot. Okay, so clearly not just as simple as on, off, on, off. That's not the pattern created. It's just fibbing, to imply that you can't see any of that nuance. The nuance is there to be seen. It's right there in the picture, and he's just going to pretend it doesn't exist.
With ripples on a pond. The Veritasium video has got a really good video of that.
Yes, well, so what? It's a really bad video about actually doing single photon at a time, and he found that he couldn't do it over. You're arguing that if you want a single photon at a time, you make the experiment happen over a very long period of time, so you can have very, very dim light. And he couldn't make it work when he allowed it to run for 10 hours instead of 10 minutes. He had to move the experiment into a 5-second window to force the event to happen. So he couldn't get it to work the logical way to do the experiment. It didn't work, implying kind of clearly that what's the difference between doing the experiment quickly and doing the experiment over a long period of time? Well, the difference is your likelihood that they're not single photons, that there's more than one photon in the experiment. That's what shortening the time means you're likely creating. And so it's just a garbage video. 8 million or 10 million views, and it's junk science.
Clearly see some bits where the water ripples are bigger and some places where the water ripples are smaller. So here it is. This is the two-slit diffraction pattern that Young observed.
This isn't what Young observed, so again, that's just not true. It's not what Young drew as an experiment. He drew basically the output of a single slit. This is a double slit pattern. He didn't draw this. He didn't understand this. It's not part of his analysis. He made the slit so infinitesimally small there couldn't be a second pattern, because he basically said two of the surfaces are so close that they're a single point source. They can't create any interference because you can't draw a line from those two surfaces that are going to be out of phase. You can't make one of them a full wavelength longer, because the two surfaces are so close to each other that any line I draw, even a line from this point to this point, to this point, all right, I draw a line from here to here and a line from here to here, and even then I don't have a wavelength of difference. So I can't even make a wavelength of difference when I have the two lines right on top of each other. Clearly, separation is going to help that problem.
Now, often in textbooks you will see, you might see a photo of it like this, but often you will see this represented graphically as an
Right, and you'll see it represented completely inaccurately. The double slit looks like this, and they're going to draw it like he's going to draw it, which is the single slit.
intensity plot. So if I take the middle of it down here, I'll do my best to draw straight. So this is roughly the middle of the pattern, and you'll see that I've already drawn a line on here on the x-axis. What we can do is sort of plot the intensity, sort of plot the brightness of the light as a graph. So here, the brightness is very bright. And then a bit further along, so in the middle, it's very bright. A bit further.
So no precision going sideways here. So he's basically just going to draw these x's, and he's just going to completely ignore that extra gap. So the extra gap is going to get lost, gone. So the envelope is now going to be destroyed. Even though it exists, it's not going to be rendered.
Along, it's very dark. A bit further along, it's bright. It's not as bright as it was before, though. Maybe it's there. Then we've got no brightness. Then
so he just placed the place where there's a double no brightness. Okay, it's a twice as big not off. I mean off. He just said it's a regular off. It's not a regular off.
well, it's dimmer than it was before, something like that. Then no brightness. Then it's even a little bit dimmer. So we're getting this pattern, and if I try and mimic that pattern, the pattern should be pretty much symmetrical.
So again, he just wiped out the double off.
Then we could try and join that up. Let me turn the lights on. So now we've done that.
So this is how you convert the double slit into a single slit.
We can take the screen off now. So now, what we've got, let me zoom in a little bit.
So you can sort of see the distance, but you barely, just because of the way he put his little X's and O's in.
Is we've got an intensity plot, which looks like a mess, but don't worry, we'll sort it out. So here it was bright.
So you can sort of see that there, some differences in the distance here, but again, this, he's lost the envelope.
And then it went dim. So we've got a lot of brightness, then no brightness. Then a bit that was a bit dimmer, then it was dark. Then it was a bit dimmer, then it was dark. Should be roughly symmetrical.
So right in here is where he's breaking it, and right here he's breaking it.
Good.
Okay,
so this is an intensity plot
distance,
where the x-axis is like...
and he's not letting us see it. So again, so he just completely destroyed the envelope pattern. He destroyed 2 of the surfaces, the pattern they're contributing, wiped it right out, and is just pretending this is about a single slit with the widest opening, and that's all he's doing here.
Excuse me. That is distance from the center of the screen. Distance from the center of the screen. The y-axis is like light intensity. So you need to know what this intensity plot looks like for the Young's double slit experiment. You also need to know what it looks like for a single slit too, but we'll do that afterwards.
Right. So again, it'll be the same for the single slit, except this maxima is double. Okay, this center part is going to be the double part. He'll probably pay attention to that, but he didn't pay attention to the fact that you have this big gap of off here and a big gap of off here, and he didn't pay any attention to that. All right. So just really bad. I might as well finish it.
Now, the spacing between 2 of these fringes, the spacing between the middle of this bright one and the middle of this bright one here, that's called the fringe separation. So
right, and he just basically cheated the fringe separation entirely by killing this double negative.
Distance from one bright fringe to the next bright fringe is called the fringe separation. However, instead of just doing it between one fringe like that, you're better off measuring between like 10 fringes or something like that. And actually, if you look...
yeah, I know. You'd be better off paying attention to the difference, that there's a huge difference in the separation between this one and this peak. There's twice the distance between those peaks.
If you rewind the video and have a look at those fringes again, you'll notice that the bright bits are quite wide and the dark bits actually seem to be quite narrow. So you're actually better off measuring between the minima.
Right, and he doesn't explain that either, you know, why that is, but that has to do with the tolerances of the light. That is, you can be a lot out of phase and it still is a photon. So clearly it's making photons that are a lot out of phase, and they have to be a tiny percentage that are perfectly out of phase are the actual darks. So you can be quite a bit out of phase and still make a photon, would be, I think, the reasonable conclusion.
The dark bits. So if I draw on here, here's one dark bit, 1, 2, 3, 4, maybe doing 5 of them or something like that. So measure 1, 2, 3, 4. I didn't quite get 5 though, so I'd have to do 4. 1, 2, 3, 4. I'd be better off measuring that distance there and dividing by 4 to get my fringe separation.
So isn't that, you know, it's just kind of so stupid, because obviously that average just destroys the envelope pattern. So again, it's just wrong. It'll give you a wrong answer. That average will not be the distance between this peak and this peak. The average will be a different number because you're not including the fact that you have doubles in here. And those doubles will increase the average value. So your average value will not be consistent with either the envelope distance or the peak distance. So it won't be of much use because it technically won't be accurate.
Just to really demonstrate how the practical works, it's very straightforward when you're using a laser, it's really easy. How it works, what the pattern looks like, and how you might see that represented in a textbook as an intensity plot like this. Next lesson, you're going to do the experiment, you're going to do some measurements, and by looking at the formula, we're going to be able to deduce the wavelength of the laser we are using.
Yeah, so they'll get the wrong number because if they're going based on that average isn't going to give them the right answer. But anyway, they'll just pretend everything's just fine, because that's all they do, is just pretend everything's just fine when they really have broken the physics. All right, so I think that's enough of Let's Play videos. Now, I'll see if anybody has anything to say, give you a little bit of time, but if not, then I'll just move along. So, just might as well look and see if there's anything really interesting. He does some slow motion films. I haven't looked at all those yet, and the last one he made was 3 years ago. So, ruler hanger. So this is some sort of moments experiment with a ruler hanger, so I guess we probably should watch that. So I'll move the comment section out of the way again. So no comments, whatever.
Okay, in this video I'm going to show you how to make a very quick and simple paper hanger to enable you to do moments experiments like this. So for this you will need the sheet printed off, which you can get from examsmasher.com/moments. There's 2 per sheet, some scissors, a glue, and a hole punch. And that's about it. It's a pretty quick process. There's some instructions on the sheet. Basically what you need to do is cut around the shape.
All right, well, this is...
You don't have to be too precise about your cutting.
It's forget that. All right, you're just folding it over the ruler, and then you have your hole punch that you'll hang it from a nail or some kind of object, blah, blah, blah.
Try and make sure they line up quite neatly. The one bit where you want to make sure you've got the hole punch lined up nicely along that center line. It's the first time I've used this hole punch to do it, so we'll see if I manage to do a good job or not.
It does seem like a complicated hole punch, but whatever.
Yeah, not bad. So you want to hole punch it with the hole centered nicely along that line. And that's it, you're done. So then you just shove your ruler, your meter ruler through here, and the idea is that it makes your moments experiment a bit easier to conduct, because this is inherently stable when you hang it from the punched hole. So now if I show you the real thing.
So the real fulcrum is just this little tiny top of your paper. Okay, so how much that gets pushed in, who cares, really depends on how small a pin you connect it to. Like a thumbtack or something would be a very small fulcrum. It'd probably be okay, but paper is really not great because paper does bind and stick.
This out over here. Let's just get it nicely focused. There we go. Here you have it set up. So here I've got it set up so that the ruler is suspended from exactly its center point. And if I take these two weights off, the first thing you want to do is check that your ruler hangs horizontally. If it's not hanging horizontally, it's not a big problem. Get some blue tack and stick some blue tack to one end or the other until it hangs nice and horizontal. If you want to check if it's horizontal, you could always measure the height from the bench to the ruler at one side and the height to the other side. Then after that, the easiest way I find to hang things off it is to get about 15 centimeters of string and just tie a little knot in it. And you can use that to hang your weights off it. And then you can go around doing whatever experiment you want, either by hanging multiple weights from different sides.
And again, you get the completely proportional relationship between whatever this number is and the mass differential will end up giving you the same thing. So it's a momentum converter. Alright, so I don't know where moments come into this exact part of it, but whatever.
Of the ruler and moving them until it's horizontal again. Or alternatively, you could be trying to balance it with only one weight, in which case you're going to move.
So you obviously are balancing it with two weights again. You're just putting the weight in the sense that you're just changing how much of the lever's on the other side. So it's still the same weight equation.
Ruler through the support until you get it to balance horizontally again. Doesn't look very horizontal for you because of the angle the camera is at. Sorry about that. There we go. So that's how to make the hanger, and once you've made the hanger, you can do your experiment.
Alright, so that was disappointing. A little bit too rudimentary and not very informative. So it probably was a good time to give up because I guess he was making videos for third graders. I guess he got demoted to grammar school or something. Anyway, this Hooke's Law one is, so it just basically, it's not unuseful. I'm just saying it's probably also kind of just boring because it doesn't say much. I mean, it just basically points out that at the beginning and at the end of spring compression, it doesn't really obey Hooke's law. The line isn't straight as you'd like it to be. So you have to be kind of careful about the fact that it's more linear. It's less linear certainly at the maximum compression or maximum stretching. That's where you really have to be careful. You don't want to maximally compress a spring and you don't want to stretch a spring beyond its deformation point. Alright, but that's enough of that. All right, so let's see. They got one comment. It's probably hello or something. Blah blah blah. Hey, yeah. Well, okay, whatever. It's not physics. Hello, hey. No, not physics. It's a fact. It isn't. You know, just saying. So we'll give you a couple of minutes to say something, or we'll call it a video again. See, well, guys, so I can go look and see who's here. How many people is here? 10. So we didn't do much better. 9, it says. So I had 8 like a half an hour ago, so it hasn't improved much. So that's disappointing, but it's the way of the world, frankly. The way of the internet. The way of the Googleplex. Yeah, the Google net. So I think I've established once again that if you believe in momentum as a real thing, and then you believe in the conservation of momentum, you really can't believe in kinetic energy, because it obviously has to be. Levers do it, hydraulics do it, gears do it. They create free energy by your formula. Yeah, well, they weren't. I'm sorry. Yeah, I mean, there's no point in asking me. Yes, I went and, you know, there are videos I've already, either I've played in a video or it's not terribly informative. I mean, I don't recall what links were yours. Like I said, I got this link from somebody else. I thought it was your link, but I guess not. Let me just find the link. What the hell is that? That's not the right folder. It says it is. Oh, okay. So let's see. I'll see what this one is. I can't remember. Copy link location. I'll go there real quickly and we'll see. But I'm just saying, yes, it's crap I've already seen. Yeah, this is the Arbor Scientific, complete useless crud. Okay, starts off with a Newton's cradle and then moves on to just smashing two balls together. I think I actually did play this video. So yeah, I mean, obviously you're just smashing two things into each other. They're not going to be able to convert their momentum into actual movement, so you have to deform something, or you have to heat something, or the energy has to go somewhere, and they're just demonstrating that, yeah, it makes a lot of heat. You know, so what? It's not useful. This doesn't show how there is or isn't something called kinetic energy. This is a vague definition. There's no I'm collecting the energy and I'm multiplying the energy and I'm comparing the energy, kinetic energy, to momentum. You need comparisons between kinetic energy and a momentum. Just saying, making comparisons between potential and kinetic energy don't mean anything. So it's just useless crapola. So anyway. All right. I'm just fine. Send links, but I mean, I'm not gonna, you know. If I find the link useful, you'll see it in the video. If I don't find it useful, you won't. But I don't need to discuss it, I don't think. Where the hell's the live window? That's not it. What the hell is this shit? Is physics philosophy? Oh, clearly the way it's done by other people it is. Oh, okay, yeah, I ruined my live window. That was a mistake. Yeah, is it still there? Shit. Can't do that, Gary. Yeah, that was a big mistake. Alright, let's see if this is the same stream. Oh, it says it is. Oh, I got more viewers by not having a video play, right? So anyway, I don't know. Okay, I got your... Okay, you know, there's a point where you're just going to irritate the fuck out of me with this pandemic bullshit about every communication you have with me. You have to verifications and all this bullshit. I'm not going to do all that crap. So if that's what you're waiting for in life, forget it. You're not going to get it. You know, God damn. you know, there's no point in me having personal conversations with people in the frickin' text, okay? Just no point in that. I have to let everybody in on it. Okay, let's go look at the stupid links he sent that don't have anything to do with the subject and blah, 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 blah. No, I don't need to do all that context. I'm not talking to just you here, you know. This video is supposed to be watched by other people. This isn't like a personal chat thing. Whatever. People tell me, hey Gary, you gotta quit being nasty to people who like you. You gotta be a nice guy. You gotta do all this crap. But it's like, you know, come on. This is stuff I shouldn't have to explain to you. I'm not interested in chatting about anything but the physics itself. So any other subject isn't really why I'm here. I'm here to discuss physics. Now, I will indulge in some of this other crap, but when I do it, don't expect me to be in a good mood, because it's not what I want to do. So, I don't know if the other video, I guess I was still streaming on OBS, so, I mean, I don't know whether it what it did to the video, so we'll have to see, I guess. So you just have to be really careful how you're using the word kinetic energy. As I have explained, they use the word to compare active energy to stored energy. So they'll call it kinetic energy versus stored energy. You know, they'll do some stupid thing like that. That's a different subject than the difference between kinetic energy and momentum. If you want to find a valuable experiment, you have to find an experiment that compares kinetic energy to momentum and shows that here in this experiment we conserved the momentum, but we made a bunch of free energy, kinetic energy. Now, obviously that one's going to be hard to find. You can find the physics girl where they say we destroyed a whole bunch of energy. That's the one you can find. And that sort of illustrates the point also, because we're supposed to believe that you can make sounds and you can make metal bend and you can make stuff burn and you don't have to use any momentum at all. So you can do that experiment. You put a certain amount of momentum in, you get a whole bunch of heat out and you get a whole bunch of sound out and you get a whole bunch of other crap out and you get your momentum back. See, they'll show you the experiment where they, you know, convert the light thing into the heavy thing, but they won't show you the experiment where they convert the the heavy thing into the light thing, because that's the one that makes the free energy, and that's the one they have no hope of explaining. Alright, 2-minute warning. Maybe less. Physics talk or else. I guess it's the or else. Alrighty then. So until we get more viewers, there's just not too much point. But you know, it's a good video. So I played a bunch of crap and explained a bunch of crap and there. So did my job and such. So till the next time and such, so forth and whatnot.